All right, so in this section, we're going to focus on model assessment metrics and methods. Obviously, if you're producing a predictive model, you're going to want to have a sense of how good it's doing, or the quality of the predictions, to actually be able to justify that the results you're getting are actually meaningful. So accuracy assessment is a very important part of the process and should never really be skipped. Okay, so we're going to break this up into kind of three broad sections. We're going to look at multi-class assessment metrics, and then some specific examples for binary classification and probabilities, and then we'll look at some metrics for regression. So there are different techniques depending on the type of classification that you're performing. Okay, so generally we assess multi-class classifications using the error matrix or confusion matrix. These terms are kind of used interchangeably. I prefer confusion matrix, but it's personal preference. Okay, so the idea here is that we have a set of validation or reference data, and we're comparing the classification to the prediction, right? So the standard in our field in like remote sensing is the columns will be defined relative to the reference data, and then the results or the classification or predictions will be the rows. So for example, this cell represents, this is set up as a proportion, so the proportion of samples that were forest and were correctly classified as forest. These were the proportion that was grass or pasture and correctly classified as grass or pasture, so on and so forth. So effectively that diagonal here is going to represent the correct answers, so they were labeled to the correct category, and anything off the diagonal are going to be errors. So one thing nice about the error matrix is that it doesn't just give you a sense of the overall error rate, it also allows you to understand what categories were most confused or where the sources of error actually lie. So for example, there were no cropland points that were incorrectly mapped as forest. However, there were some pasture grassland that were correctly mapped as cropland, or some cropland they were incorrectly mapped as pasture or grass. So it looks like there were some issues of confusion between cropland and pasture land, but not really between crop and forest as much in this example. So what we're going to look at in the next set of slides is what you can kind of derive from this matrix to kind of summarize the results. So there are a few measures that are based on kind of the overall model performance, so overall accuracy, but then you can also get measures of class level performance as producers and users accuracy. So we're going to look at those now. Okay, so as a kind of global measure of model performance, we generally look at the overall accuracy, and that's just effectively the proportion or number of samples correctly classified divided by the total number of samples. So if we go back to our confusion matrix, it's going to be the sum of the diagonal divided by the sum of the entire table. So number of correct divided by total number of samples. So that gives you a sense of overall accuracy, but it'd be nice to have like a finer grain measures to look at accuracy or performance for individual classes. And that's going to be our users and producers accuracies, which we'll look at in the next slide. We'll look at in the following slides. Okay, so users accuracy is a measure of commission error. So that's basically a sample was included in Class A when it was supposed to be in Class B. So for example, we labeled this class as forest when actually it was supposed to be pasture, for example. Mathematically or statistically, that represents the probability that a feature classified on the map actually represents that category. So that's commission error. Producer's accuracy, in contrast, is a measure of omission error. So again, a sample is supposed to be in Class A, but was incorrectly classified to B. So for example, this thing was supposed to be an example pasture land, but we incorrectly called it forest, right? So omitted from a class, or for omission error, producer's accuracy; included in the wrong class, commission error, user's accuracy. So if you use the standard setup that we use in remote sensing, where the reference data define the columns and the predictions define the rows, then you're going to use the columns to get the producer's accuracy, and you'll use across the row to get the user's accuracy. If you would flip them, it'd be opposite. So that's why it's good to keep it standard here, right? And we'll look at a few examples of that in a minute. Okay, so basically for user's accuracy, using our standard setup, it's going to be the correct samples for the class divided by the row total for user's accuracy. And then for producer's accuracy, it's going to be the correct samples divided by the column total. Okay, so kappa is another measure. So sometimes you can get samples correct just by random chance, which can maybe inflate the reported level of accuracy that you're actually so it's unrepresentative of the actual reality. So basically, kappa offers an adjustment or correction for accuracy that takes into account this chance agreement. So it's basically chance adjusted overall accuracy, and we'll look in a minute of how that's classified or predicted. Okay, so here's some examples. So here I just switched from the proportions to counts because it's a little easier. So to get overall accuracy from this table, we'll sum up the diagonal. So 91, 80, 81, 87, 69, 73, and 96 there. Divide by the total, which is 600. And that works out to 0.828 as a proportion, or as a percentage, 82.8%. So of our testing or validation samples, 82.8% of those were correctly classified. And then for kappa, we're doing a chance adjustment for that. So how that works is you take your total number correct and multiply that by the total of the table. So there's our corrects times the table total, or 600. And then you divide that by the table total squared. And then for both the numerator and the denominator, you have to have this adjustment factor. And to get that adjustment factor, you take each row, column, total combination multiplied and then add them together. So it's 100 times 113 plus 100 times 100 plus 100 times 101, so on and so forth. So basically total correct times total minus that factor over total of the table squared minus that factor. In this case, that works out to 79.4. Generally, we report kappa as a proportion as opposed to a percentage. Okay, so let's just spend a minute and look at the user's and producer's accuracy. So let's go back for a second. Remember, user's accuracy is commission error, and producer's accuracy is omission error. Okay, so let's start off with producer's accuracy down the column. So again, this is omission, right? So all these samples were supposed to be in the forest class. These ones were correctly put in the forest class, where these ones were omitted from it, right? So this is the omission error. So 91 divided by 100, 91%. So omission error. And then for commission error, these samples were incorrectly put into the forest class. So it's commission, right? And so we'll take the sum 91 divided by 113, or the row total, 81%. So in this example, just comparing the classes, it looks like we were having the most difficulty separating like the cropland and the developed classes, and pasture to some extent. Water was mapped pretty well. Forest wasn't bad. But you can see depending on whether you're looking at omission or commission error, those patterns are going to be interpreted a bit differently, right? So in short, users and producers accuracy allows us to look at class level accuracies and specifically quantify errors of omission and commission, and we can look at, by the error matrix, what classes were most confused. Here's just another example with binary classification, so just forest versus not forest. Basically, it's the same thing. So overall accuracy, we take the diagonal, 94 and 85, divide by the total, which is 200. So that works out to 89.5%. To do kappa, we're doing the total correct times the table total, and then the table total squared, and that correction factor, so 100 times 109 plus 100 times 91, right? And that works out to 0.890 in this case. And then again, our producers and users accuracies, our omission errors here for the classes, and our commission errors here for the classes, producers, users. Just to be honest, I really don't like the term producers and users accuracy. To me, it's not really clear what that means. I kind of wish we would just call it omission and commission or whatnot, but we don't. Just as another note, I just realized, so really users accuracy is 1 minus commission error, right? And producers accuracy is 1 minus omission error. So this is defined as an error, and this is defined as an accuracy. So it really should be 1 minus commission and 1 minus omission error. Okay, so a note about kappa. In the field of remote sensing, there's been a lot of critiques of its use. I don't want to get into all the nuts and bolts about why it's been suggested that we not use this metric anymore, but I agree, and I think so I would suggest to not calculate and use the kappa statistic in analyses. I don't think it really adds any information over overall accuracy. It can be a bit misleading. The way it's actually trying to adjust for chance agreement is flawed. If you're interested in reading about this issue, I suggest these papers. So this by Gil Pontius and Malone's for an International Journal of Remote Sensing, and this more recent paper by Giles Foodie. They do a good job of explaining why this metric should be abandoned, and this paper actually suggests some alternative metrics. Okay, so how do you actually make a confusion matrix using the caret package? All right, so to do that, we use the confusion matrix function, and you give it the predicted class from the model, so the model output of the predictions, and the actual classes from the reference data, and that will generate a confusion matrix. You can also do a confusion matrix from the training data using the withheld folds. And that's done with the confusion matrix.train function. We're not really going to get into that, but I just want to note that if you set up a cross-validation process, you can get back the error matrix for the cross-validations with this confusion matrix.train function as opposed to confusion matrix. Note that there are some other packages that provide accuracy assessment. So for example, the EPA-display package provides the cap function, which produces kappa. You basically create a table and then feed that table into this cap function. And then more recently, as part of the tidy models ecosystem, there's the yardstick package, which can calculate a wide variety of assessment metrics. Another option is diff-R, which is actually produced by Gil Pontius and his colleagues, and it implements some of the kappa alternatives that they've suggested, which we're really not getting into here. So if you're working with binary classification problems, it's common to actually see different terminology. Now, the error matrix really isn't that different. I mean, you're basically having actual and predicted, and you're just differentiating the errors. But it's just traditionally a different type of terminology is developed. So I thought it was important to at least discuss that because that can be a bit confusing when you're new to this. Okay, so here we have a generic binary two-class confusion matrix. So I set this up the same as we did with our multi-class confusion matrix. So the actual or reference classes define the columns, and the predicted classes define the rows. So basically we have true positives. Those are samples that were true in the positive case and were predicted to be true. So correctly predicted as positive. The true negatives were correctly predicted to be negative. So they were in the negative class and they were correctly predicted to be negative. A good way to think about this is things like medical tests, right? So say you get a test to see if you have you have a certain virus or something. So a true positive would be if you have the virus and the test correctly said that you had it. And then a true negative would be if you didn't have the virus and the test correctly said that you didn't have that you didn't have it, right? So those are both correct. The incorrect is the false negative and false positive. So for a false negative, it should have been true, but it was predicted as false, or it was supposed to be yes, it's predicted as no. So in our medical test example, this would be saying you actually did have the virus, but the test came back negative or said that you didn't have it. And then the other type of error is a false positive. So it's supposed to be no, but it was predicted as yes. So again, for our medical test example, this would be saying you had the virus when you actually didn't have the virus. Okay, so using these four results, so true positive, true negative, false positive, false negative, we can calculate a series of derived metrics. You can do like overall accuracy, for example. So that would just be the same as for the confusion matrix. So for precision, here's kind of the new terminology. So both precision and recall are relative to the true class, right? So the positive case. So the precision is going to be true positive divided by true positive plus false positive. So you're effectively taking the true positive and dividing by true positive plus the false positive. So that's kind of across the row. And then for recall, which is also called sensitivity, those mean the same thing, is the true positive plus the false negative, so we're looking down the column. So if we go back to our confusion matrix real quick, effectively the producer's accuracy going down the column, that's going to be equivalent to recall, and then going across the row is going to be equivalent to precision, right? So, and that's explained. I'm just going to pop ahead to this slide for a second. So recall is effectively producer's accuracy for the positive class, whereas precision is user's accuracy for the positive class. So again, this is just like commission, omission, error, right? Okay, so that's precision and recall. They're effectively user's, producer's accuracy for the positive class. It's just different terminology. The F1 score is a way to combine these metrics into one measure. This is the harmonic mean of precision and recall. So it's basically 2 times precision times recall divided by precision plus recall. So it's just combining those two metrics. More generic, we have F beta, which means you can change this value here, and it changed the relative weights of precision and recall. Okay, so then we have a couple other measures that are relative not to the true class, but to the negative class. So we have specificity, and that's going to be basically the equivalent to precision, but for the negative class. So it's the true negatives, the corrects for the negative class, divided by the corrects plus the false positives. So again, we're looking kind of down the column here, so that's going to be like your producer's accuracy. And then going across the row is going to be true negative plus true negative plus false negative, and that's known as the negative predictive value or NPV. So if you take if you calculate the precision, recall or sensitivity, specificity, and the negative predictive value, those are effectively all the users and producers' accuracy for the positive and negative class. And then F1 score is effectively just combining the two positive class metrics, or commission, omission, error assessment rates or whatnot. Okay, this is a table from this publication that kind of summarizes this. So some of the common assessment metrics. There's more in here that we're not discussing. So I'm just discussing the common ones. So again, overall accuracy in terms of the binary assessment metric terminology is basically true positive plus true negative divided by everything. So all true and all error. Recall is the producer's accuracy for the positive class. Precision is user's accuracy for the positive class. So, and then specificity is producer's accuracy for the negative class, and negative predictive values user's accuracy for the negative class, right? So that's kind of how those things relate. Again, there's other measurements here that we're not going to look at. Okay, so those were metrics for assessing both multi-class and binary classification output. So now we're going to look at metrics for assessing continuous or numeric prediction, so effectively regression output. Okay, so RMSE, or root mean square error, is probably the most common metric that we use to assess to assess regression models. So to calculate RMSE, you basically take the correct value from the reference data and subtract the prediction for that data point. So the difference between the prediction and the actual value is the error, or what's commonly referred to as the residual. So effectively what you're doing is you calculate the residual for each of the testing or validation data points, then you square those, sum them up, divide by the number of samples, and then take the square root. So this is kind of like an average error across all the data points, and that's known as root mean square error. So let's imagine you were predicting like a percentage, right? So you would take the correct percentage minus the predicted percentage. So the unit of measurement there is going to be percent. Then you square it. So now the unit is going to be percent squared. Then you divide by n, so there's no unit there, so it's still going to be percent squared. And then when you take the square root, that's going to take the units back to percentage from square percent. So what that means is the root mean square error is going to be reported in the units of measurement. So if you're predicting like a chemical concentration in parts per million, RMSE is going to be in parts per million. If it's percentage, it's percentage. If it's income, it's going to be income, or dollar amount or whatever. So it's in the same units as the dependent or the variable being predicted. Mean square error, or MSE, is just root mean square error without the square root applied. So you do the same math, but you don't apply the square root at the end. So since you don't apply the square root, it's going to be in the square of the units of the thing you're predicting. So percent squared, parts per million squared, dollars squared, whatever. I tend to prefer to use root mean square error because I think it just is more easy to interpret the results when you're in the units of the thing that you're predicting. Okay, to calculate RMSE and R, you can do it just using the basic R math like on vectors. It's pretty easy to do that. I show you how to do that in the example modules in R. But if you want to calculate it in a more automated way, it can be done using the metrics package in the RMSE function, which so effectively you just feed it a vector of the actual values and then the predicted values, and it spits back the single RMSE estimate. So that's the metrics package. You also use yardstick too, which is part of the tidyverse. Okay, another common assessment metrics for regression problems is R squared. So you might be familiar with R squared if you've looked at linear regression equations and whatnot. So effectively, R squared is a measure of the proportion of the variance in Y, or the thing that you're predicting, that is explained by the model. So to calculate the total variance, you basically do the total sum of squares. So to do that, you take each data point, you subtract the mean value from it, so that's the mean, and then you square those and sum them up. So that's the sum of squares is basically the sum of the squared variance, right? So so the larger that value, the more variability is. The smaller that value, the less variability that there is. Okay, so basically how we would do that with our training data is we would take each data point, take its actual measurement, subtract the mean of all the testing data, right? Or the testing or validation data. So take each data point, subtract the mean of the data set from it, square them, sum them up. That's the total sum of squares. Okay, and then the residual sum of squares, the difference is instead of using the mean, you use the prediction. So effectively now you're summing up the residuals. So you get the residual, square it, and add up all the residuals. So this is the total variance that exists in the data you're predicting, the dependent variable. This is going to be the remaining variance that the model didn't explain. So in order to actually get the proportionate explained, you basically just take the total sum of squares, all the variance, so this, subtract from it the residual sum of squares, or this, and that gives you back the variance that was explained, and then divide that by the total sum of squares. So that's going to end up being a value between 0 and 1, where 0 means no variance was explained, and 1 means all the variance was explained. So the larger the number, the variable, the better, right? And since this is basically just a ratio, there's no units, right? So we have, this would basically be in the unit, the square of the units of the thing you're predicting, and then you're dividing by the square of the units. So the units drop out, so it's going to be unitless. So it's just an index or value from 0 to 1. And it's just the proportion of variance explained. As a side note, if you're doing multiple regression where you have more than one predictor variable, you're supposed to adjust R squared because of like the inflation. So effectively you can get improvements in R squared even if you're really not getting model improvements when you're adding predictor variables. So this adjusted R squared applies an adjustment to correct for that. So you basically take 1 and you subtract from it the R squared, and then you multiply that by n minus 1, where n is the sample size of the number of of validation samples. And then you divide by the number of samples minus the number of predictor variables minus 1. And that'll give you adjusted R squared as opposed to the regular R squared. Okay, so the last set of metrics we're going to look at are based off of not using a hard decision boundary, but using the resulting class probabilities across a variety of decision thresholds. Okay, so what we're going to look at first here is this concept of a receiver operating characteristic, or ROC curve. Okay, so imagine you have a distribution. So this represents the probability distribution for the predictions of the negative class. So this is for like a binary classification. And this curve represents the predictions for the positive class, right? So this is the x-axis here would be the predicted probability of being in the positive class, right? And then the curve relates to the, how many data points are in the that are represented at that probability, right? So if you want to perform a classification, you have to assign a threshold that represents true. So generally what we say is 0.5. If the probability of being in the positive class is 0.5 or higher, then that's going to be mapped to the positive case. And then if it's not, then it's going to get mapped to the negative case. And we do that for both the positive and negative samples. And going back, that allows us to effectively generate this table, when then we can generate all these assessment metrics from it. So the key thing is that all of these are based off a single decision threshold or probability threshold for the positive class. And you could get different measurements depending on the probability. So if you could say, well, it has to have a probability of higher than, say, 0.6 or 0.7 to be the positive class, and that's going to change all those numbers, or could change all those numbers. Another option would be, instead of using a hard threshold, is that you could use a variety of thresholds and summarize that, and that's effectively what we're doing here. Before we get into that, let's just talk about what true, false, true positive, false negative, true negative, and false positive represent in this distribution. Okay, so this is our decision threshold. So all the points ahead of this line is going to get predicted to true. Everything back here is going to get predicted to false, right? So the true positives are going to be the portion of the true curve that got mapped as true. So this red area here, that's going to be your true positives. The portion of the true curve they got mapped as negative, the green area here, that's going to be your false negative. So this curve got partitioned into true positives, correct positive classifications, and then false negative or incorrect positive classifications. And then for the other curve, which is the negative curve here, the false positives are going to be everything in that curve that was predicted to be positive when it was actually negative. And then the purple area here was predicted to be negative when it actually was negative, so true negative. So I hope you can see how we can take these probability distributions for the two groups, the negatives and the positives, pick a threshold, and then get counts of true negative, true negative, and false positive samples. Okay, so this explains the true positive rate and the false negative rate. We'll go ahead and that's not really that important. I think it's easier to talk about this in terms of recall and precision and whatnot. Okay, so looking at this curve, this now is moving from getting a set of metrics from a single decision threshold, and instead trying to summarize the result across like all decision thresholds. And that's done using this receiver operating characteristic curve. So the goal here is to plot the false positive rate and the true positive rate at all decision probability thresholds. And that relates basically to the specificity and the sensitivity. So let's go back to this slide real quick. So sensitivity is recall. So in this case, effectively the y-axis is recall, and specificity is going to be the x-axis. And if we go to this slide, again, we can see the specificity is the producer's accuracy for the negative class, whereas recall is the producer's accuracy for the positive class. So these are effectively looking at producer's accuracies for the two classes. And if we go back even further to when we're talking about users and producers' accuracy, that's going to be omission error. So omission error relative to the true class and the negative class. Sorry, let me get back to where we were. Here we go. Okay, so again, sensitivity is our recall. That's your x-axis, and specificity is the x-axis. So how we actually build out this curve then is we get the specificity and the sensitivity measurements not at one location or one decision threshold, but across all decision thresholds. And that allows us to generate this shape or curve. Okay, so we now have this curve, but we'd like to be able to summarize that into like a single metric. So generally what is done is the area under the curve is estimated. So so here we have this scaled from 0 to 1 for sensitivity or recall, and then from 1 to 0 for specificity, just specificity. So this is scaled the opposite direction, right? Because it's 1 minus versus sensitivity. Okay, so the area then for the if a line hugged up this corner, so that would be basically an area of 1 times an area of 1, so the area under the curve would be 1. The closer it gets to this line, this 1-to-1 line, if you split this graph in half, you're going to have 0.5 on this side, 0.5 on this side, so this represents an area of 0.5. So basically, if you get an AUC around 0.5, that's considered equivalent to just taking like a random guess. You're not really getting strong performance. The closer you get to 1, the better the performance. Generally, this is assessed similar to like a college grading scale. So 0.9 to 1 is considered excellent, an A, 0.8 to 0.9 is a B, 0.7 to 0.8 is a C, 0.6 to 0.7 is a D, and then 0.5 to 0.6 is an F. It's really hard to get lower than a 0.5 since that's basically random. One thing nice about this is it's unitless and it's in the same space, so we can compare these AUC models to compare or AUC values and ROC curves to compare models. So here we have a couple. This is for predicting slope failures, and we have a couple different models. So we have one using all the available predictor variables. The blue line, that's red. The blue line here represents using just the terrain-related predictor variables. Then the green is all the variables but the terrain variables. This is using variables associated with distance from roads and streams. And then this is only soil and lithology variables. So what we can see just looking at this curve is that we get the best performance from using all the variables or just using the terrain variables. They're actually pretty close. If we take out the terrain variables, the model performance actually decreases pretty substantially. Okay, so in short, a larger value is better. Another option is the precision recall curve, which is different from the ROC curve. So remember with ROC curve, we're basically plotting recall on the y-axis, and then, I guess go back to for a second, so recall or sensitivity on the y-axis and specificity on the x-axis. When we do a PR curve, instead, what we're doing is comparing precision and recall as opposed to recall and specificity. So this is all going to be relative to the true class. So again, let's go back real quick to this slide. So we're going to recall is the producer's accuracy for the positive class, and precision is the user's accuracy for the positive class. So you're effectively getting omission and commission related, we're assessing commission and omission related errors for the positive class. Okay, so that's just another curve, and then similar to the ROC curve, you can calculate an area under the curve, and it's generally assessed or interpreted similar to how we assess the ROC curve. So 0.9 to 1 is an A, 0.8 to 0.9 is a B, and so on and so forth. Okay, so let's just look at a side-by-side comparison of these two curves. So again, for the ROC curve, the x-axis is going to be 1 minus specificity. That's how we get the 0 to 1 scale instead of, if we just had specificity, it'd be 1 to 0. If we do 1 minus specificity, 0 to 1, right? So again, that's true negative over true negative plus false positive. Yeah, and then you can see that how that relates to this here. I encourage you to take some time to look at this. I tried to combine all this information kind of in one place. And here, recall is true positive over true positive plus false negative. Here, we're effectively using this, so the x-axis and the y-axis are the same. They're both recall, and then here we have precision as opposed to specificity. So just side-by-side comparison, they're both used for binary classification problems. Note that there are multi-class versions of these metrics, curves and AUC values. We're not going to get into that. It's really just like a one versus many, but there are ways to use it for multi-class. Here we're just looking at binary. It's generally going to show that the ROC curve can be flawed when the data are highly imbalanced. So you do have different numbers of true and false samples. That's partially because the ROC curve only considers producer's accuracy or omission error. It doesn't take into account user's accuracy or the commission error. So generally speaking, if you're interested in assessing both the producer's and user's accuracy relative to the positive case, it's good to use the PR curve alongside the ROC curve. And the PR curves tend to be less misleading when you have imbalanced training data, whereas the ROC curve can be misleading. If you want to calculate this inside of R, the PROC package is a good option. The ROC function produces the ROC curve. You basically provide the response, which is the probability for the true class, and I guess that's backward. The response is the class, the correct label, and then the predictor is the probability relative to the true class. The plot.roc will then plot that curve. You just feed it the result from the ROC function. AUC calculates ROC, the area under the curve, and you feed it in the results from the ROC function. And there's also a statistical test available to compare ROC curves statistically. If you want to produce you can also produce these curves, both PR and ROC, and the associated area under the curve metrics using the yardstick package, again, which is part of the tidyverse. If you want just some notes on some useful papers for looking at for trying to get a better grasp on classification methods, their use cases, their flaws, when they can be misleading. I really like this paper by Tharwart. Here's a link to it, or there's the citation. It does a really good job of summarizing this. Here are a few other good papers, just if you're interested. We're not going to talk about these in detail. A couple different series of papers there. So this is a pretty heavily researched topic, so there's a good bit of literature on it. Okay, so we're going to stop here now. In the next video, we're going to talk about how we can optimize these different hyperparameters.